Hello, I'm Kris, and welcome to nfpack element, a case study in which we'll explore different approaches towards grabbing the nth element out of a variadic pack. If you were expecting a talk about std, next element, I will have to disappoint you. Sorry about it. But this talk is way more exciting. It's way more exciting because it has magic. Why it has magic? Because there are templates. So hopefully you will enjoy that as well. So if you have any questions, there'll be a lot of, as I pointed out, magic. Feel free to ask, and I'll try to do my best to answer. So hopefully that sounds okay for you. So let's begin and see what we're talking about. So first, we'll talk about the motivation, why that's important, and why we would like to do that, what that gives us. We'll take a look into different solutions towards grabbing the nth element. There are a lot of ways to do that since C++11, since we get the variadic packs. Some of them are more compelling than the others, so we'll compare them. After that, we applied to tuple, because that's one of the reasons why we want to understand that. And then we'll do the benchmarking. Actually, we'll just see the benchmarking. I've done them before. Across different solutions, as well as different languages. So we'll compare how C++ actually compares to Rust, NIM, dlang, and other languages. And after that, we will sum up. When there will be a dark background, it means that there is something which I personally found important and something to remember about the talk. And all the examples are powered by Compiler Explorer, so anything is actually compilable, and you can check it out. Okay, so motivation use cases. I'm working for high frequency trading companies, so performance matters for us. So we use a lot of templates on daily basis. So for example, like 1,000 element of tuple is not a biggie for us. So performance of the compilation times is important in that case. Obviously, there are different use cases like reflection. You can imagine that we have a struct which we want to reflect on, introspect, and after that we want to serialize it to JSON and stuff like that. So all of that requires a lot of magic with the templates, and if you have a lot of them, compilation times also matters, and readability as well. So that's what we'll try to take a look here. So motivation from the code perspective to actually grab the nfpack element for the tuple is a bit different than obviously from the use cases perspective. The reason is that when we have a tuple of 1 to 3, it's a tuple of 3 ints, right? So we try to get an int out of it that's ambiguous, and it's gonna compile. I wish that would be the error message, but it won't be as good. So alternatively, std provides the get with numbers, so we can get 0, 1, 2, blah, blah, blah. All of that works. What will happen if you get a 3, for example? Yeah, it won't compile. It will say something definitely not even close to that. It will be like 10 pages of error messages. But the outcome will be that there is something wrong. What? Probably no one will know. But yeah, that's the idea. So besides that, when we have this tuple of 3 ints, one of the ideas behind that's the algorithm you can apply. That's a common pattern in the C++17 when we get the index sequence and we can apply it to the get. Anyone knows what kind of algorithm I'm talking about from std tuple? Everyone is saying apply, just for the record. So std apply is a kind of doing something like that. How we use it? In that case, when we want to print elements out of the tuple, we do print, we get the function which takes a variadic arg, in that case, and does the print with the fold expression. And the index sequence is just to be able to enumerate the number of elements in the tuple. So we have to do this tuple size, blah, blah. As you see, it's quite verbose. That's why we have std tuple. And the only thing which we have to do is the lambda. So that's the motivation for the nfpack element as well. And that will obviously print 1 to 3. So where we are now. So getting first element is actually quite easy in the language already. We can do something like that. We have a lambda, we get the first element, and then we do args, and we return the first, and we propagate it, populate it with args. So that will just return us the first one. So language supports the first, getting the first element out of the box with the Lambda expression. Nothing really difficult here. Last element is also supported. It's because the comma operator with the expression will give us the last one. So if you have here 1, 2, 3, the result of that will be 3. So if you apply the default expression over that, we do args. It will give us a warning that is unused value, but in the end, it will give us the last element. And if you want to avoid the warning, we can assign it to itself. And and that will give us and that will give us the last element as expected. So first and last, quite simple. There's no that much magic involved besides the fact that it's kind of clunky. But what if you want to do first and last? We can actually combine both approaches and get the first out of, the lambda and last out of the rest, and do that ... and we get the first and last. So that's still okay. So that's the current state. This nice proposal, which I wanted to mention because I think it's really important and will improve the getting first, last, and then element as well. So it's the proposal which it's called structure bindings can introduce a pack. So it's basically the structure over the Varadic pack, and we can take the first element and do TSS. We have to put the name here, but that will give us the first. So nice, it will work on aggregates as well. So that's pretty cool. We can do the last, very similar as well. We do TS last. So I think that's kind of really cool because usually we cannot do that because the arguments are greedy. So we cannot do that. The Rx has to be at the end. We can also do what is pretty cool actually with that proposal, first and last at the same time. So we have first, TSS, last, and that will give us what we expected. But all of that is just the first and last. What about the env? The env is actually more complicated. That's why we are actually talking about it. So how to do that? We'll take a look into different approaches. But that's the goal. The goal is to be able to implement, in the end, the get for the tuple. So we'll do that by, and I'm not having any, value categories here on the slides, just for the slides, so don't worry about them. It's more about the TMP stuff. And that's the goal. The goal is here to explore all the possible, not all the possible, the solutions which are kind of known and cool to show, and apply the env-pack element out of this Rx . So that's the definition which I'm going for with this exercise, that the env-pack element will return element at n position from a variadic pack. So, sorry about that. So objectives here, how we will compare, the solutions. We'll compare whether it supports different types, because that's important. There are solutions which are cool, but it won't support different types. We'll compare how much magic is involved. As I pointed out, there's a lot of TMP. Some TMP is better than the other TMP. So we'll compare that. And performance, if there's an overhead, we won't expect any runtime overhead because we do static asserts in the end, so wouldn't expect that. But what is really important, as I pointed out before, is the compilation times. That's what we really want to measure. Whether, for example, for small tuples, it's better to have that solution, or even, whether the std tuple is fast, or how it compares to different languages. So let's see about the solution. So there are three main solutions, ideas, which I'm here going to explore. First one is that we do this magic as an overload. So we have this auto dot dot dot, which will have the number of n minus 1 elements before the nth. Then there is the nth, we return the nth, and then this auto dot dot dot, which we just ignore. So that's a very common solution, one of the best, in my opinion, to follow. The other solutions, this one is very different in a sense, that we create a struct or a type which has an ID, which is an index, and also a type, so like a pair or of the ID and type, and a struct inherits from a lot of them, n of them actually, and then we try to get the one which is associated to the nth element which we are looking for. So that will give us the type associated from the inheritance which we have the type for. So, and that's not even the magic yet. And obviously there are language features as extensions we will take a look into, and especially circle language, which will be also awesome. So just to sum up, the solutions, there are like 10 of them, I think, so let's go through them. stdra, that's just for as a showcase. It doesn't support all the types, because stdra, as we know, can only be one type, but it's a good use case of the syntax which we would like to aim for, and hopefully we'll get there eventually. Recursion, mainly to show that it's not great, but who knows, we'll see. There'll be like arg expansion, concepts expansion with C++20. There'll be library examples, Boost MP11. That's a really good TMP library, very well optimized for the compilation times. I did this for you. I did Boost Preprocessor solution. I spent half a day so that you don't have to do it. Don't encourage anyone to do it, but we have it. Specific language extensions. So Clang, Louis implemented the type pack element at some point, which is a compiler intrinsic for Clang, which gets the nth element very quickly out of the pack. So we'll compare that. Who knows about Circle? Yeah, there are a few hands. Circle is a compiler which is kind of extension to C++, and it has really good TMP. I would say it's a TMP powerhouse, and maybe C++ will get there ever in the future. And we'll also take a look into this proposal, which is super exciting, and I think it will get in. It will change the TMP programming in C++ forever. It's based on Circle, in a sense. It kind of takes the small parts of it and allows it in C++. So we'll take a look into that. So, okay, let's take a look into the array. So all the examples will start the same way. We have an bag element. It takes args dot dot dot. Notice here is a lambda. So as a showcase, we can do the no discard on the lambdas in C++20. So that doesn't apply. If you do it on the left side, that actually doesn't do what you think. So that might be important. And how we do it. So obviously, that doesn't work for different types. But what is cool about it is the fact that the syntax is pretty cool. We have args dot 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 of n. Obviously, we have to do stdra because we need to get the nth element out of the array. So I don't know. Who likes the syntax for that? Is that OK? If you compare that to stdget, I think it's better. If you compare to others, I think it's pretty cool. What about the stdra? Well, it doesn't support different types. So if you have npack element of A, 2, and C, that ain't gonna work because there are different types. We're out of luck. So what about the readability? I think it's really flexibility, sorry. That doesn't work, as pointed out. But it's quite readable, in my opinion at least. It depends how many characters you have to type in order to get the nth element. Sometimes with Boost Preprocessor, you have to, maybe not type, but you have a lot of characters in the end. Is it performance? So I'm not having any claims, so I always ask the audience whether they have any ideas, because without measuring, I was surprised by most of the results either way. So would that be fast to compile or slow? We won't know because I didn't measure. Because it doesn't satisfy the requirements. But it's the language feature, so I would assume, like we have different language features to compare. Sorry about that. If is anyone interested, I can measure that. Okay, so let's go to actually a proper solution which actually satisfy the use cases. So recursion is a very common, naive approach. Here, the recursion will be done with concepts because it's just nicer. It can be done without. So if we have the requires clause here and n is equals 0, that's the base case. We return the arg element, which is the first one. Otherwise, we recursively go again with n minus 1 with the args, and that will, recursively just take out the first one until we at the end with 0. And the base case is here really important because otherwise it will never compile. So that's it about the recursion. Quite easy to implement in my opinion. It does satisfy the requirements, so that's pretty cool. It's flexible because it works with all the types. It's kind of readable if you compare it to other solutions. Is it slow? Any guesses? Slow, fast, recursion? Slow. Okay, well, I will keep that in mind. We'll judge afterwards. So, but the recursion might be done differently. I just wanted to point out that actually there is a difference whether you have an overload or whether you do a solution with if cons expr. So that's in C++17, we can do that. And if cons expr is the same solution. We still do it recursively, but we don't have a different function which has a different overload. We do it in place, in a sense, we call the same function. And we do if cons expr for the base case. So we will compare that solution as well. It's kind of the same as before. There's nothing really special. Any ideas? Would be faster than recursion 1 with the overload, or will be slower? Same. Same, faster? Faster. Okay. I don't know. Okay, so for the next solution, I just wanted to quickly, I actually showed that before, but it's like just to introduce it as a good pattern, immediately invoked function expressions. So if you want to, in C++, that's C++20. If you want to unroll something like in place, instead of doing a for, which will be actually difficult unless we have this template for proposal, we want to execute a function expression here, in that case, multiple times, but it will be unrolled. So there's no for and jump in the assembly, it will be just n times unrolled. That's the way we can do that, a bit verbose, I'd say. But we have the make index sequence, and we call immediately invoke lambda, and then we have to do this expression, fold expression over the expression, and these ISs with the void is just to do the pack expansion because the expression doesn't depend on the n ISs, so we have to do that magic. So I just wanted to hint with this proposal, which I mentioned before, that's actually much simpler. So we can do make index sequence, which is also destructured into ISs, and then we can just call it, like the bottom part is still not ideal, but the first part is actually pretty decent, I'd say. So we can have make index sequence and then call it and expand it. So how that looks in the assembly when we call it with 2. Notice here that the assembly will not have any jumps. It will be just put twice, and that will be efficient if we want to do it for the performance reasons, but might be inefficient if you do it for really big n elements or very often. So always measure. Okay. So next solutions will be still based on the arguments. So we'll apply this in the immediately invoked Lambda expression. So we have index sequence just in order to get the NSs. And then we do this one of the solutions when we have the arguments being expanded. So the decal type of void star here is to get the n-1 elements before the one which we actually care about, and we need the pointers because it's a void, it's not the regular type, so we need the void pointer. And when it's auto dot because we don't care about the rest, and we return the one in the middle, not in the middle, the nth. So that satisfies our requirements. I would say it's a bit of dark magic. I don't know whether you can write it on your own just like that. But if you can, I'm impressed. So is it faster? It doesn't have a recursion. Is it faster than recursion? Yes. OK, bold claim. No, I wouldn't say so. OK, so very similar solution to what we actually had before. With C++20, we can do that with concepts. So we have a concept which is just always true. Doesn't really matter. It takes the type and the ID, because we need that concept only to expand over it, and with the terse syntax over the pike element. So we go through all of them as before. And the idea here is that the prefix is the concept, right? Like that's the terse syntax, like when you have a concept, when we have the auto, when we have the name. So here we have the concept, which is always true, always satisfied. Then we have the auto, we don't care about the name. It's kind of like similar to the previous solution, just modern. Then we have the arc, then we have the and we return the arc. So that's the solution. It satisfies the requirements, works with different types. It involves a bit of dark magic, since we have to do concepts. OK, so how does it compare to other solutions? Would that be faster, like a concept giving us anything here versus the void star? I would assume that here in the claim before that would be faster with recursion. But would that be faster than void star? No? Same? Slower? Who knows? Yeah. Hard to say. I actually don't remember. No, I actually know. Just messing with you. So MP11 is a library. Who actually been using MP11 before? Just a few people. If you are trying to do TMP these days before C++20, I would really advise to learn it, because it's quite easy and it's really performant. We can do a lot of things with that library. So I won't be doing an intro, but it has functions, like meta functions, like MP take, MP list, MP something, MP something always. So MP list here is just the list of types, like a type list. Then we have the MP list, which of the arcs. So we do MP list, the call type arcs, and we do take n elements. So what we will get in the TSS on the top, we will get the nth elements. And why we need that? Because we want to do exactly the same as before. So we have the TSS then we have the arc, then we have the auto, and then we return the arc. So it's the same kind of solution as before. Like we had void star, we have a concept, and right now we just have the proper types. And all of them are very similar in spirit, but behave totally differently if it comes to compilation times. So requirements are satisfied. So I would say it's a bit more readable than the previous solutions, and the reason being is that, well, it hides a bit of magic behind the library. Not much though. Okay, so there's a hint here. It's it's well optimized. That's a boost claim. So you know the question: faster, slower, the same? Who knows? I don't care. No opinions? Probably similar. It's kind of the same kind of approach, right? So can assume that it will be similar if it comes to the compilation times. But also, like when I'm asking, like no one actually corrected me, but it depends, right? It always depends because, like, am I asking below 10 elements? Am I asking on like 1,000 elements? I'm asking in general the trend. Okay, so I know you've been waiting for that. That's why you're actually here. Yeah. So how we do the preprocessor, I don't know whether you want to go through that, but the idea is here that we actually do the recursiveness with preprocessor. So we'll expand it from I equals 0. That will take the first one. I equals 1. We'll ignore the first one, take the second one, and blah, blah, blah. So that's the idea. And then the solution. I wrote it first time without any compilation issues, just for the record. So we start with the nth arc. The first sign here is just to ignore the arguments because they have to be passed. So then we do nth pike element. That's a macro which generates that function somehow with the boost pp repeat, which has the limit associated to it. I think it's 1024 or 256, depending on the version of the boost. It's not unlimited. But the idea is here that we will generate accordingly to, because we have one more pp repeat. So we go from the nth, we decrease 1, and we do call the other one. Because the first one is just to generate all the functions, and the other one is to generate the arguments and ignore them. So the inc and dec is just increment, decrement, and pp repeat is just repeat. And hash is to join things. Important stuff to know these days. And then we can undev it, so that we can forget about it. But what is important with that solution, I think, is the fact that we always generate all the functions. So there's not like, at the point of the instantiation, we will generate as many functions as we need for different types. We generate them up front. So that has a compilation results. It affects the compilation results because, for the element, like if we want to take a first element, we still have to generate, 1024 functions. If you want to take 1023, it's still the same. So, but it works. That's good. I tested it. And yeah, what can I say about the readability? I don't know. Probably not the code which we want to write on daily basis, but I would be willing to write it in the library if it was the fastest. But will it? That's the question here. Will that be the fastest solution because it's the preprocessor, so it knows everything up front? Okay, so yeah, I don't know. Maybe, I guess we'll see. Definitely won't blow up the compiler. Okay, another solution. So right now we move into the solutions which are using not the overload kind of approach. So here we'll introduce something like we had before with the prefix for the concept. That'll be like struct any, which takes the type and takes also the value. We do the same thing, and here is the magic. So we create a struct. Notice here that it's anonymous struct because that's also valid. So it's a struct colon. So we like in the dark magic, so that makes it even more obvious. So we have the any, which takes the type and takes the index. We do ... And we pass the objects to it so that aggregate will be instantiated, the value of it. And then we do this nice trick that we have the immediately invoke Lambda expression where we propagate the struct. And we try to get the nth element out of these inherited elements which we passed through the struct. And that will either give us the any of given type for that ID, or it will not compile and will give terrible error message. But if it pass, it will give us the any of tn, and then we can just return the t value. So that's a totally different approach than before, but still valid. And it's still passing the requirements. A bit of dark magic here. Doesn't have the recursion. But is it faster than the previous solutions? Can we compare that? Any intuition about that? No intuition whatsoever. Yeah, I'm on the same boat. Okay, so type pag element is yet another solution which we have. We'll try to apply the same. That will be only for the Clang though. So GCC or MSVC or any other compiler doesn't have it. But the premise is the same. We just have the args as a struct, but instead of doing the inheritance and then deduce the type out of n, we can just do the static cast because we actually grab the nth element out of the variadic pag because we know exactly where it's supposed to be. Because we have this type pag element, we take the nth out of any ... So any ... it has all the elements, and we take the nth, and when we know that it will be inherited in the struct above, so we can static cast it and take the value. I hope that makes sense. I've done all of the experiments so that you don't have to. So it's a Clang extension, so it doesn't work on all the compilers. That's probably not ideal. But it's a compiler intrinsic. So one thing one can expect from compiler intrinsic that would be fast, right? I would assume that. Or something is complicated and it can be implemented in the library. But in that case, it could. So I think it was added because it's supposed to be faster. So we'll see. And I pointed out it before, Circle. I am huge fan of that language because it's really powerful if it comes to template metaprogramming. And it's really expressive if it comes to grabbing grabbing nth element, or you can do a lot of things with the variadic pag, which we can only dream of. And how you do it? So I pointed out before, like args, like stdra had really cool syntax, right? It was close, and that's why I was saying about it, because that's what the syntax is. So I think like we have a lot of solutions which are dark magic, no one could actually understand, but I think this one, it's like if you had to guess, what would you guess? That it will give us the nth element? Potentially? Yeah, I don't know what else it could return, so I'm interested, you can grab me after. Okay, so I would say that if it comes to like how many characters you have to write, you can't do much better. Maybe you could avoid this ... but probably that would be kind of not intuitive. So that's a language feature. That's even better. All of that is language feature. And I think you'll be blown away by the results. I was. I still am, actually. I'm still in the shock how slow or fast that is. But it's not the end. There's hope for C++. And as I pointed out, this proposal, which is based on Circle, so if you get it, I think it's proposed for 26, or maybe 23. I think 26. And spot the difference. Yeah, basically, if you get it, that would be the syntax. I just wanted to notice that with C++11, there was a proposal which actually had the same syntax, and it was rejected because it was confusing. So we get std get out of it. But yeah, maybe it will get in. It has also, this proposal has additional things which are super cool. Like you can, do you know like Python slicing with these index square brackets? You can do that with this proposal as well with templates. So you have ts ... and you can just take -1 to take the last one or stuff like that, or like slice it. It's pretty cool. So regarding that proposal, yeah, I think like if you get it, that'll be awesome. And in my opinion, we can't do much better if it comes to that. So if you get it, sorry, there'll be no more talks about it. Maybe that's good. But yeah, so I don't have a comparison to that solution as well, sorry. No one implemented it. I spent some time, but not enough. No, I didn't. But okay, so right now we did all of that in order to get the tuple out of, to get the nth element of the tuple. So a question to the audience: why we don't have that? Wouldn't that be better? Like, or even square, index operator would be better in my opinion. But let's say why the get is not a member function of the tuple? Why it's std_get? Like I would like to say tuple get like map empty. Any ideas? Okay, I'll show the secret. So that would work. T get of 0. But if you have, dependent template context, you'd have to write this .template in order to call a function which is templated. And yeah, that wasn't desired because, I don't know, if anyone would actually write that and would know about it, that's hard to learn. So if you have also like the auto as well, that would also require us to write the template. So that's why we don't have it, and we cannot have it at the moment. Universal syntax would actually help with that if you know this proposal from Bjarne about that, so that we can call the member function as a free function as well with the same syntax, but we don't have it, so std_get is what we have at the moment. So if you take a look into the tuple, that's the requirements we had. And what's the easiest implementation of tuple is actually to use lambdas. Like that's basically a tuple implementation. Obviously not the full, because the full one has like 100 constructors. But the idea here is that we return a lambda, which will apply the function to afterwards. So that will fit really nicely with our solution for the nth pack element. So how do we do that? So we have a get. So you have a get here, which takes the nth element and the t, and what we return. And so the t here is the function. And the function will be called, and we'll expand it with the args.dat, because that was expanded, that will be the function will be called. And after that, we call the nth pack element of n args.dat. So that's how we can implement the get. We still need the nth pack element because we are in the Varadic pack space, and we have the n. But the tuple is actually quite simple and quite powerful. Someone actually measured that a few days ago because someone posted on Reddit that this solution compiles faster, like 2 times faster than the tuple which we currently have. But I would assume that no one implemented all the constructors and requirements for the tuple, so it's a neat trick, I'd say. So just wanted to also point it out, there's like, I don't like tuple interface, and we don't have context per parameters, they would solve a lot of things. But since we don't have it, we can generate them by using integral constants. So if you have a function which takes auto, you cannot pass 1 to it, like as an integer, because that won't be concise proof. But you can pass integral constant of 1. That'll be totally fine, because that's the type and the values in the type. So then, the get didn't fly very well because we had the template. But if we actually would use the square bracket, we could do that. So here, that's actually the wrong bracket, but not the parents. That's supposed to be square brackets. So the tuple with n_c, that's how we get the integral constant, actually doesn't require the template, so it's pretty cool, and that's how we can get the nth element of the tuple. So tuple 1, 2, 3, and we want to take the first one, we just get it by square brackets of 0_c. So it's kind of similar to the map interface. So I think it was pretty cool. And how you implement that? So in that particular example, never do that at home. You inherit from the tuple, and you do the square bracket operator with the n. Notice here that the n has to be an auto. That cannot be an int, because that wouldn't work. Auto will be here an integral constant. And then in the get, that'll be converted to, at compile time, to the value. And we propagate this, and that will give us the nice element. And how we implement this thing? So since C++ 14, I think, we have this UDL syntax, which allow us to do parsing. That's the generic one, which we require here. So we parse the characters which are provided. I did that with this proposal, and we return an integral constant of int. And here we just do, characters to an int, basically to the value. And with the proposal and also with circle, I wanted just to show how the tuple could be implemented, because it fits on the slide, doesn't have all the constructors and the requirements. But if you have the Varadic pack as a member parameters, that would just work. We have no unique address, just in case for the TSS will be 0. And that's it. That's like a tuple. Store the TSS, get the TSS at nth, voila. And if you get that proposal in, that also will be potential implementation of the tuple. So just wanted to also point it out that with tuple you can do a lot of manipulation. That's a C++ 20 thing which you can actually do. So at compile time, so get might be implemented with the drop and take with the ranges. That's like powered by the library. But notice here that we have static assets here. So the tuple is of compile time actually values. And notice here that we have the lambda because we have no context parameters. So that has to be propagated like integral constant. Here we just do lambda. And that will just work out of the box. It will give us the nth element with C++ 20 and ranges. And you can do even more. You can do stuff like that, for example, with the tuple. So, and you can do it at compile time and runtime. So you have a tuple, you filter elements which are odd, you reverse them, you drop them. All the fun parts of the ranges are available. So I think like the template meta programming and the future for it is quite bright, because I think that's actually who could write that, who feel comfortable with doing that versus the previous solutions. I would assume more people, right? I don't know who's comfortable with Preprocessor, but maybe, I don't know. Okay, so I hope that was kind of clear. Obviously, the goal of the presentation so far is not for anyone to remember all those tricks. It's just to measure them and see where we're at. And that's important because, I remember all your guesses. It's on record, so we'll see. But yeah, it's always important to measure because it's surprising, and always measure in the production-like environment I couldn't do that because I don't have a use case, but I did my best to not to do micro benchmarking in that case. So we measured the readability as well. So just to sum up, there was a lot of dark magic with the arc and concept expansion. Boost preprocessor, I'm not going to talk about. Compiler extension for the other part. But what is important, I think, is that the circle and the proposal is something which we aim for because that's where cool stuff actually might happen. And you see how many possibilities that opens up for us. So there are different use cases depending on what we are working on. Sometimes there is a lot of tuples of less than 20 elements, and then it's important whether the tuple less than 20 compiles fast. That's often the case. Sometimes we have a few generated tuples or types which we want to compile. And sometimes we have both. That's the case where I'm in, so we'll see how that compares. Just wanted to point out, and C++ obviously has limitations, and I'd say, like MP11, I pointed out, is really optimized, but we're still in thousands. We cannot compile, millions of elements in the tuple. You wonder why? Anyone would want that? Grab me afterwards. But OK, so how we do the benchmarking, I use Luidion MetaBench. If you want to check it out, it's metabench.ch. And the idea here is that we use Ruby to generate the, I think that's Ruby. Yeah. So median of 3, it's like we run it 3 times so that we don't have too much spikes because I was checking emails all the time because it takes so long. npack element will be something which we generate. So that will produce npack element of 0, 1, npack element of 0, 1, 2, blah, blah. And then we generate each CPP file. What is also important that you can mark the parts of the code which you want to measure. So you don't have to measure the includes and other things. It's just grabbing the npack element. OK, so let's see the result. I don't know, you probably see that some of them are better than the others. So let's just take a look. So those 2 big ones, and that's the recursion. So I think one learning already is don't use recursion because it won't scale. However, on the smaller scale, that doesn't matter as much. Like here, on like 20 elements, is a lot of noise here. But it doesn't matter as much as, oh, actually, you don't see it. Sorry, I have to go here. So for the small elements, I would say that's noise. I couldn't get it to really compute really good result, and that's for GCC 12. But what is important here is that I asked you before whether the recursion has actually a difference with overloads and ifcons expert, and actually does. The yellow one is the ifcons expert, a bit faster. And if you take a look into the last element, which is like, it makes a bit small difference, but you can see that some solutions are much better than the others. So if you pick the wrong one, you might not be satisfied, and the difference is huge. But that's GCC 12. So where are we at? We have recursion, which is out of the question. There's nothing really to, we can disable that. So if you disable recursion, notice here that the next one is the preprocessor. Sorry, didn't win. The best solution is for GCC is arg expansion. So that was the solution when we had the void star dot. That's the best for GCC. How does it compare to Clang? And that's GCC 12 and Clang 15, so like the newest part. We have kind of the same results. Recursiveness and preprocessor, they're out of the question. And then we have to disable them. So if you disable that and that, second time, and if you disable the preprocessor, we see that most of them are they scale in quite similarly. So the fastest is, so here you see MP11, it's quite good. Type bug element is quite good, but the winner is arc expansion or concept expansion, depending on how many elements we have. And on the smaller scale, if you look into the elements which are smaller, we see that it doesn't matter as much. Obviously, it matters if you have like millions of them, but the comparison is kind of in the noise. We see that the fastest ones are the arc expansion here. But you would have to really measure in the environment you have. Okay, so let's see circle. So circle will have funny solution because all of that is the same, but I don't know whether you see the X line. It's also circle. So if I'll disable, Sean, the author is always saying that it's flat, no matter what. I can just disable all of them. Yeah, that's the variation, but you can see that it's just going to like way below anything else. So you can see why language feature as a tuple is actually important feature. So just to highlight the nth park element solutions. If I can type it here. So not a clear winner because I couldn't get the really good results here, but I would say all of them kind of are well optimized in that case. Recursively, don't use that. Please avoid that. That's never a good solution. Multiple overloads are slower than the if-cons expert, so that's something which is maybe worth noticing. Clever solutions scale quite well, which is pretty cool. But all of that, it doesn't matter, because circle just destroys everything, it's flat. And if you get that solution, that proposal in the end, depending on the implementation, maybe it will get flat as well. So for tuple, I did the same experiment. Just wanted to compare whether the tuple itself has optimizations, which we can see, and that's doing the get on the tuple. And what we can see here is that for GCC, actually, the tuple is the best. So we have to disable these outliers here. But this solution on the bottom is the tuple. So yeah, congrats to GCC. They optimized the tuple to be the fastest, faster than the solutions which were provided so far. That was the case not for a while. Last time I gave the talk before, that wasn't the case. So maybe they've seen it. So maybe good job, Kris. I don't know. But what about the Clang? Clang actually is very similar if it comes to the benchmarking. Like a lot of them are really close, and one of the best is Tuple. Tuple was actually much slower in Clang 14, so there were really a huge optimization which happened since then. What about Circle? Same old story. You just look at the bottom. That's the main part of it. Like everything scales somehow, and Circle just is flat. That's why this talk wouldn't make sense if you have Circle, because all the components were just flat. Okay, so just the highlights: recursiveness, avoid. Clever solutions, they're okay. GCC and Clang, are pretty cool. So I wanted to point out that circle tuple is circle tuple itself is really fast, but tuple from the libc++, which is also supported in circle, is actually much slower. So it shows how it actually is faster to do the language feature. Okay, so don't have much time, so and just to show off how the quality of compilers, that's kind of what is checking here, nfpag element, there were the best solutions. So GCC, 7 seconds. That doesn't really matter. That's for 200 elements. 7 seconds, GCC, Clang for 4 seconds, circle, okay. Tuple, 7 seconds, 5 seconds, and circle flat. And the worst solution is also interesting because that's also always the recursion. So we can actually compare the compilers, which one compiles the same solution the fastest. So I would claim that there's something wrong with GCC and Clang in comparison to Circle, because the same thing just compiles, I don't know, 5 times faster, 4 times faster. So yeah. If anyone see that, please notice. And how does it compare to different languages? So any predictions? How good? Obviously, Circle doesn't matter if we don't compare that. But we compare Clang, in that case, to like Rust, NIM, D language, and others. Any ideas where we at if it comes to the tuple, especially for the big number of elements? Are we the fastest to compile, the slowest? Well, I'm surprised that there are no big claims.
There's a faster range, so there is a lot of energy that goes into optimizing C++ ecosystem.
Okay.
Much more than the other languages. So Rust will probably.
Okay, interesting. No, it's totally valid claim. So tuple below 20 elements, I'd say, and that compiles the whole binary, I think. But you can see that most of the solutions are kind of similar. I think the Zig language, it always takes longer because it's kind of slow by default to compile, but it scales very well. And we can see here that out of all the languages, Circle seems to be still the fastest, even to Rust and Clang and DMD is the D language. So that's for elements less than 20. But how does it compare to more than 100? That's the interesting graph. So this, like, exponential line is actually Clang. So yeah, up to like maybe 20, we good. After that, all the languages scale. Like they scale, right? It's like a bit slower, but they scale. Circle is obviously on the flat line, doesn't matter. But yeah, Clang and GCC as well. I don't have the results here, but I can assure you that it's the same case. We just don't scale very well at the moment. If you get this proposal in, definitely we scale much better. So just to sum up, from the readability perspective, all of that is quite clever and fun, and we can play with it, and that's not the production code, I would say, for everyone. So we should hide it by tests and libraries. MP11 is a great example of that. There's more magic there than I actually shown, and the interface is quite nice. What about performance? As always, avoid the recursion. That's kind of like the main part of it. If you compare the fastest and the slowest, recursion the slowest, Circle flat. That's maybe what is important of this talk. And I didn't even compare things like if you want to sort elements. Like in Circle, if you want to sort the Varadic pack, you just say t ... like in in the parents and .unique. That's a language feature as well. So there's a huge difference in performance as well. So I believe at the moment, in use cases where we have a lot of big tuples with a lot of elements or type lists, lack of language features actually hurt in C++ because it's kind of, even if you don't use it, I don't like showing diagrams where we kind of embarrassed by it. So I think if we apply that proposal, that would be awesome. And we'll be in the pair of other languages. So yeah, let's pack some more language features. Thank you.